Hi everyone, my name is Jacqueline McCleary. I'm here to talk to you today about the wonderful potential for galaxy cluster weak lensing analysis when we use imaging taken in the stratosphere. Just so we're on the same page, galaxy clusters are structures that consist of hundreds to thousands of galaxies and their hot gas, all bound together by gravity. They span 2 megaparsecs in diameter, and even a small cluster weighs 100 trillion solar masses. This is a rather pretty example taken from my own research, cluster Abell 2029. This is a big cosmology conference, so of all the possible cosmological probes, what makes galaxy clusters useful? Well, because they're so large, they are dark matter dominated, and thus an ideal place to study dark matter and its relation to cluster baryons. There are all sorts of galaxies living in clusters, all engaged in diverse activities like star forming, merging, driving powerful jets, and so on. So, clusters are a great place to study galaxy astrophysics too. Clusters also don't really start growing until Z of about 1, when dark energy begins to dominate the expansion rate of the universe. So their evolution is a good probe of dark energy as well. Different models of the universe, different cosmological models, predict unique cluster mass abundances and number counts. So, measuring the abundance of clusters as a function of redshift and mass constrains cosmological models, which we usually parameterize with things like sigma 8 and omega m, the overdensity of the universe in a sphere of 8 megaparsecs, and the matter density of the universe. How do you get these required masses? How do you weigh a galaxy cluster? Well, through an application of general relativity. You can measure galaxy cluster masses through their gravitational lensing signal. To explain, here's a picture I borrowed from the internet and fixed slightly. Any foreground mass, like a cluster, bends light rays from a distant galaxy, moving the apparent position of the source on the sky, magnifying it and stretching its image. The stretching of the galaxy image is proportional to the foreground mass. We can reconstruct the foreground mass distribution by looking for correlations among these gravity-induced distortions of background galaxies. Gravitational lensing is the preferred way of measuring cluster masses because it makes no assumption about either the state or the composition of whatever matter was doing the deflecting. When they think of gravitational lensing, most people think of something like Abell 2218, shown here, with its dramatic arcs and multiple images. This is the strong lensing regime. But most of the time, we operate in the weak lensing regime, where the distortion is too small to be measured on any one galaxy. It's only 1 to 2% of the intrinsic shape of a galaxy image. So why do weak lensing analysis at all? Well, it is a much more common feature of galaxy clusters than strong lensing. Strong lensing systems like Abell 2218 are actually quite rare. Weak lensing is also better for studying mass concentrations in the outskirts of clusters. Strong lensing is best at studying the core of galaxy clusters. It's a small signal, so measuring a cluster's weak lensing signal requires lots of well-measured galaxies. This means deep imaging and as little optical and atmospheric blurring of detected objects, aka the PSF, as you can manage. So what does cluster weak lensing signal look like? This is an example from my research, Abell 3218. The image on the left is a deep observation of a galaxy cluster, Abell 3218, in visible light. The weak lensing signal of this cluster is shown on the right as an intensity map, where lighter color means more weak lensing signal, and thus a higher surface mass density. The units of this map are actually signal to noise. You get the right panel by carefully measuring the shape of every single galaxy in the left-hand image, and averaging the galaxy shapes as a function of distance from some point in the image. If you want more details on this process, I have some references at the end of the talk. And just in case you wanted to see them superimposed, Here is the weak lensing signal, the convergence of Abell 3218, superimposed on its bright cluster galaxies. So we went over why weak gravitational lensing is an excellent way to obtain cluster masses. But because weak lensing is so small, you need to measure a lot of background galaxies to detect it, which means observing a single galaxy cluster for a long time under excellent conditions. Large surveys just don't have this kind of time to devote to their whole survey area. So cluster cosmology efforts generally rely on easier to measure observable quantities that are good proxies for cluster mass. Examples include X-ray temperature and emissivity, the richness of a galaxy cluster, i.e. the number of member galaxies, and SZ flux, Sinyavs-Vildovich flux. Various examples are shown in these two figures. Richness here, true mass M200 here, and here are a few X-ray derived and SZ derived quantities as well. These mass proxies must be calibrated with the true cluster mass, which is where weak lensing comes in. The success of cosmological parameter constraints using galaxy clusters hinges on the accurate calibration of this cluster mass observable relation. We need good weak lensing masses. So, on this note, I want to introduce the idea of doing galaxy cluster surveys from the stratosphere. Meet SuperBIT, the Superpressure Balloon-borne imaging telescope. SuperBIT is an actively stabilized imaging system consisting of a half-meter telescope and a CCD camera inside a series of nested gondolas. The entire platform is suspended from a balloon which flies at an altitude of 36 kilometers. It has already had several successful test flights, the most recent of which was in 2019. Its 30 to 45-day science flight is scheduled for 2022 out of Wanaka, New Zealand. So why go to all the trouble of launching a telescope from a stratospheric balloon? 3 words: stability, transmission, and depth. SuperBIT flies at 36 kilometers, above 99% of the Earth's atmosphere. That means we don't have to contend with factors such as clouds. In fact, SuperBIT's PSF is nearly diffraction-limited, about 0.3 arcseconds, and stable over the course of our observations. This stability has been demonstrated in test flights, as you can see in this panel here. By the time that you're in the stratosphere, the atmosphere is so thin that it's essentially transparent to visible light. This means SuperBIT experiences almost perfect transmission from the near UV to the near IR. Finally, sky brightness is quite low at these altitudes. Coupled with SuperBIT's near diffraction-limited seeing, this means that even with our little half-meter mirror, SuperBIT can expect to reach source densities of 60 galaxies per square arcminute in just 3 hours of observation, shown in this panel here. SuperBIT's design choices have been made to optimize gravitational lensing analysis of galaxy clusters. Its diffraction-limited imaging results in well-measured galaxies free from the blending and smearing that plagues ground-based surveys. Its excellent photometry, particularly in the blue and near UV, reduces uncertainties in the determination of photometric redshifts, more on this later. And its large field of view, 350 square arcminutes, and depth will make it easy to acquire the background galaxy counts necessary to detect weak lensing signal of galaxy clusters. SuperBIT offers space-like imaging at a much lower cost than space missions, millions, not billions of dollars. It also offers much more flexibility. There's programmatic flexibility in the survey design, and we can also adopt the latest and greatest technologies like cameras in short timescales before flights, flexibility not generally afforded to space missions. My role in this collaboration is building an analysis pipeline that takes us from detector images to cluster projected mass profiles using state-of-the-art algorithms for galaxy shape measurement. I am vetting the performance both of my pipeline and of SuperBIT as a whole using a suite of GalSim simulations that mimic SuperBIT observations of galaxy clusters. The simulations include realistic galaxy redshifts, fluxes and shapes, a model of the camera and optics, sky backgrounds from our test flights, and the lensing potential of your galaxy cluster of choice. This pretty figure on the top left is a simulated 3-hour observation of a massive galaxy cluster. The inset is the cluster center. The bottom right panel shows the weak lensing signal extracted from this observation. The top right panel shows the full width at half max of the point spread function as measured from simulated stars. It's small, less than 0.3 arcseconds. The plan for our 2022 science flight is to cover about 40 massive, well-studied clusters in the southern sky, more if we can get them. The clusters are drawn from the Hubble frontier fields, CLASH, RELIX, LOCUS, and others. The green shaded area in the left panel shows the sky area available to SuperBIT from Wanaka, and the letters mark the positions of clusters and the surveys from which they were drawn. So for example, C for CLASH, R for RELIX, L for LOCUS, O for other. The right panels show the redshift and mass distributions of our target sample. So why revisit these well-studied objects? What does SuperBIT have to offer? Well, there are a few things. As I've said, SuperBIT offers diffraction-limited imaging and space-like backgrounds over a larger field of view than, say, existing Hubble coverage of these clusters. So we will be able to provide new weak lensing masses for these objects, new data points for cluster mass observable calibrations for these objects. We will also be able to provide very deep blue imaging for these galaxy clusters and their surrounding sky, something essentially unobtainable from the ground. I want to talk a little bit more about SuperBIT's blue imaging, specifically the wavelength range from 370 to 570 nanometers. The curves on the right show predicted depth as a function of exposure time on a single field in various SuperBIT filters. It was prepared by Mohammed Shaban, a graduate student at the University of Toronto, using camera specs, filter throughputs, and real sky backgrounds from previous test flights. The plot on the right is derived from one of my simulations of a SuperBIT cluster observation. It uses a galaxy catalog prepared by Ajay Gill, also a grad student at Toronto, containing fluxes of Cosmos 2015 galaxies converted into SuperBIT magnitudes. Our estimates converge on the fact that in 3 hours, SuperBIT can reach a depth of 26.2 in the B filter. Getting to B of about 26 is more or less impossible from the ground, and certainly not over an area of 350 square arcminutes per cluster. Having blue photometry is really valuable in weak gravitational lensing analysis, specifically the determination of photometric redshifts and thus galaxy distances. Most PhotoZ fitting codes use the positions of the 4,000 angstrom Lyman break and or the 3,700 angstrom Balmer break to fit galaxy templates and thus get a redshift. However, the Lyman and Balmer breaks are essentially inaccessible from the ground for low redshift galaxies. SuperBIT imaging would be able to provide this coverage in these wavelengths, a new capability. Let's put this into some context. So in this panel, y-axis is wavelength, x-axis is depth. SuperBIT depths, shown in green, are comparable to Euclid survey depths. SuperBIT covers a wavelength range that neither Euclid nor Roman, still labeled W first in this plot, I'm sorry, do. So it covers a much bluer range. And Gigabit, SuperBIT's planned successor mission, is going to go even deeper. Gigabit will feature a 1.3 meter mirror and will go even deeper than the Euclid deep fields. So even in an era of stage 4 incredible cosmology surveys, SuperBIT steps in the blue and its source counts will not be matched. So even in this era of stage 4 surveys, a well-designed small mission like SuperBIT still has something to offer. We can add another data point to cluster mass observable relations, including galaxy clusters that don't fit neatly onto the existing cluster mass observable relations. Let me switch here for a second. These contour plots come from the Dark Energy Survey cluster analysis, and they show that low richness galaxy clusters seem to have less lensing than you might expect from the other part of the cluster mass observable relation, the richness mass relation. When these low richness clusters are excluded, any tension introduced is removed, and Dark Energy Survey cluster cosmology constraints match what's in the literature. So SuperBIT weak lensing masses can target these outlier objects, can target, for example, low richness galaxy clusters, and get a better handle on their masses. There's a whole other program of SuperBIT cluster science targeting self-interacting dark matter through analysis of strong gravitational lensing. Of course, we can also add another data point to cosmological parameter constraints like S8 and abundance of clusters as a function of redshift. We'll already have the data, we might as well. And of course, SuperBIT can accomplish any blue or near UV science you can think of, not least photometric redshift calibration for larger surveys. If anything I've said has piqued your interest, feel free to look up some of these references. And with that, thank you for attending my talk, and I look forward to answering your questions either in this session or offline. Thank you.